In this video, we're going to go over the last of the conditional probability problems. Now, as I read through these problems, I like to write down what they're giving me as I read it. So suppose 30% of people in my classes do all the homework and get an A. So this is an AND statement. So the probability of people doing all the homework and, which we write like this, so an intersection, and getting an A equals 0.3. So as of all the people in the class, about 30% of them do the homework and get A's. I also guessed that the probability of any randomly chosen person in the class doing all the homework is 0.4. So the probability that someone does homework is 0.4. Now, if you know that you are doing all of your homework, what is the probability that you will get an A? So that's what it's asking for, and that's a conditional because it has that if. So if you know you're doing all your homework, so you know that you're doing your homework, the part that you know comes second. And now, so it's saying, what is the probability that you get an A if you know you did all your homework? So as you read this, anytime you see that vertical line, that could be like the vertical line means if. So what's the probability you get an A if you know you did your homework? So we need to break out our conditional probability formula. And that says you find the probability of the intersection. So probability of A and H. Now, it doesn't matter if you have H and A or A and H. It doesn't matter which order you write those two things in for an and. And you divide by the probability of what's known, in this case, probability of homework. So 0.3 for the joint probability, that and intersection, and 0.4 for the individual probability for homework gives me 0.75. So again, if you know that you're doing all the homework, you would have a 75% chance of getting an A. Now, example 24. If A and B are mutually exclusive events, find the probability of A if you know B. Now, mutually exclusive events, that means you have a setup like this. You have A and B, and they have absolutely nothing in common. So mutually exclusive means nothing in common. And anytime you have something like that, then you know that the probability of the and, or the intersection, will be 0. Because again, there's nothing that they have in common. They don't intersect, so the probability of the intersection has to be 0. Now, in this situation, now let's go through and look at some math here. So the probability, we're supposed to find the probability of A given B. So the probability of A given B, well, that is equal to the probability of A and B over the probability of B. Whatever is the thing that you know that comes second, that's what you divide by. Well, we said the probability of A and B has to be 0, so we put a 0 there. And the probability of B is, well, whatever it is, we don't really know. But it doesn't matter because 0 divided by anything is 0. So mathematically, if A and B don't overlap, if they have nothing in common, then the probability of A given B has to be 0. Now let's talk about what that means logically. So if they're mutually exclusive, we know A and B can't happen at the same time or together. So they are mutually exclusive. So if we know B has happened, or is going to happen, or will happen, or whatever, don't get caught up here in your past, present, and future. So if we know that B's happened, then the probability of A happening has to be 0. Because again, we've said A and B cannot happen at the same time. So if we already know B's happened, then the chance of A happening is 0 because they can't happen together. Okay, let's try 25. Show that the probability of A if you know B plus the probability of A complement if you know B is equal to 1. So remember that little tick? That means everything that is not an A. This is A complement. It means everything not an A. I'm going to do this with Venn diagrams and then also kind of mathematically. So we start with a big sample space, S. Here's A, here's B. Okay, if we're trying to shade conditional probabilities, remember this means A if you already know it's B. So that means we already know that it's B, so we actually only care about this B part. So shade anything that's in A. Let's switch colors. So anything that's in A, if you already know you have to be in B, would be this. This would be A given B. Now let's try A complement given B. So again, we already know we have to be inside this B circle. But we want everything that's not in A. So that would be everything left over that's not in A. So A complement given B. So you know you have to be in B, shade everything that's not touching A, not part of A. So then if you know, or okay, well let's say, so then if we want to add these two together, we've shaded this little bit of red, we've shaded this little bit of green. What have we shaded? We've shaded B. But we only care about stuff in B. So we only care about stuff in B because, again, it was conditioned on B. We only care about B. We only care about stuff in B. We only care about stuff in B. So we only care about the stuff in B. And if we add the two things together, since that was an add, then we've colored all of B. So the probability is 1. So if you only care about stuff in B and you've shaded all of B, well, then you have a 100% chance that you're going to get something in B, which is all you care about. So probability is 1. Now let's do it mathematically. So the probability of A given B plus the probability of A complement given B. Well, let's write out each formula. So probability of A given B, that would be the probability of A and B over the probability of B. Plus, now for A complement given B, that would be the probability of A complement and B over the probability of B. Notice this is a common denominator, so we'd add those together. So probability of A and B plus probability of A complement and B all over the probability of B. So now for this, kind of look back at your picture again. We were shading conditional probabilities, but we could do another shading to figure out what this is. So anytime we have, here's A, here's B. If we have A intersect B, that would be this little piece here. And if we do A complement intersect B, well, A complement is anything outside of A. So anything outside of that circle, we'll do some dotted lines here. Anything outside of that circle would be A complement. Anything outside that circle. But we need to see where that intersects with B, so it would intersect with B. And here, and look, we have shaded all of B now. So A intersect B plus A complement intersect B is just equal to B. So probability of B over probability of B has to be equal to 1. Now on the exam, I don't ask you guys to do proofs like these. This is more just to kind of help you get started learning proof like these. If you go on and take the more advanced statistics classes, then you would have to do proofs like these. So for an application, let's let A denote that a child likes apples and B denote that a child is a boy. What does the probability of A given B plus probability of A complement given B mean? So more like logically. So A complement means the child, well, A means child likes apples, so the opposite of that is the child does not like apples. So the probability of A given B plus the probability of B a complement given B means what in English? Sorry, I'm just trying to get my type tool to work. So it means basically that if we know a child is a boy, because both of these say if we know the child is a boy, okay, then what is the probability that he either likes apples or he does not like apples? Okay, so we are interested in both of those probabilities and adding them together. Well, if you think about it, any boy you ask is either going to like apples or not like apples. So every single boy is going to fall into one of those two categories. So the probability should be 1. And the final last proof. So let's use Venn diagrams to find the probability of A given B if B is a subset of A. This means B is a subset of A. Subset means that it is completely contained inside of A. So A is my big space here, and then B is inside here. So we're looking for the probability of A given B. So it's saying, if you know that B happened, what's the probability that you're in A? Well, if you know that B happened, that means you're somewhere inside this circle in B. But if you're inside B, are you also in A? Yes, so the probability has to be 1. So again, if you know you're inside B and B is inside of A, then you have to be inside of A. So that probability should be 1. We can prove it. So the probability of A given B is probability of A and B over probability of B. Well, A and B, if you want to see where they intersect, where are they going to intersect? They're going to intersect in B. So that would just be the probability of B over probability of B, which is 1.